How many of you are still coming in at lunch? One or two? Whichever one, you got the option of either. Whatever one you did worse on, right? If you're gonna write it, bring your torque test so I can just attach it to it and I can do a quick change. Okay. Let it be kind today.
Thanks.
That's why I assumed that.
I know. If I do.
Yeah.
So yesterday I mentioned that you should go over. I'm gonna do this last. The handout on momentum that I gave you a while back. So,
We know that. That's the other one.
okay, the gentlemen, this one here. Go over it. I'll say that to the very last tutorial. I'll go over parts of it with you. The two-dimensional problems. Go over the two-dimensional problems in it. Okay? I'll go over some of them, and not today, but I'll say that till the end. So last night's tutorial, I went over torque. I think I will, shall I go over another one? Okay, I'll go over just a slight variation on the torque problem. Gentlemen, second time, quiet. Over it later, you have a little time. So this is a slight variation, what you're used to. Now it's still a beam, but it's a beam at an angle. Okay. Okay, that beam is being held up. Actually, I'll make this a different color. Why not? Slightly different color. Beam is being held up by that purple string. Okay, so let's say the mass, the length of the beam is 2 meters. I'm not interested in numbers. I'm interested in how would you plug them in. The mass of the beam is 100 kilograms. Tension in the wire, we'll just call it F, is 2,000 newtons. Okay, so how would you set it up? Don't tell me, but set it up. Try setting that up. You want to solve for, there's a mass here as well. Let's make it more complicated. Mass here. This here is 50 kilograms. Oh, you don't have the mass of the beam. Interesting. Okay. Okay, forget this. Say you don't have this mass. You don't have that mass. You do have the mass of the beam. You don't have the mass of the overhanging mass. So find that mass. It's a, well, I won't tell you what it is. You see that it's a beam. That should automatically cause you to think. Set up the equations that you need to solve for the mass. Go as far as you can. I'm going to give you a couple of minutes. Okay, so the first thing it should, I won't go through all of it yet, but I'll start you off. The first thing that should come to mind, it's a beam, so you have to balance the torques. I would start writing down the expression for the torques. For the torque for F is F. Don't use the cosine, use the sine of the angle at the tail. Tail is here. Sine of 78 times the length of the beam, 2. That's your torque for that. Circle it or put a rectangle around it. Torque due to overhanging mass, I'll call it tau m, is mg. So remember to include 9.8 there. Find the weight. Times the sine of the angle. The angle here. Whoa. The angle here. What's the angle? Well, we know this angle here. Okay. I'm going to draw one more. I'm going to draw the center mass there. And then the corresponding FG. The angle here is the same as the angle here. How does this angle compare to that angle? They're supplementary to each other. This angle here, plus this angle here must add up to 180. Well, look, if you don't, how did I get that? Do you agree that this angle here is the same as this angle? You see that? That angle there is the same as that angle. Okay, so this angle here must be the supplementary of that. It must add up to 180. This one's 120, so this one here must be 60. So this one's 60. That's the trick. That's messy. Okay? That's the trick. Part of the trick. So this becomes mg times the sine of 60 times the full length, which I said was 2. And then tau g, the tau due to the weight of the beam, is just Fg. We've got the mass of the beam. So it's mg, mass of the beam, times g, times the sine of 60, times half the length. Yes, you use half the length times 1. So this becomes 100 times 9.81 times sine of 60 times 1 is just as is. Doesn't change it. It's 981 times sine of 60. Circle that. Circle this. You can simplify this further. G is 9.8. But those are your torques. Okay, so I just gave you the expression for the torques. Now balance them. Balance the torques. That's what this equation says. Essentially, balance the torques. Similar to balancing forces. Write it out in terms of tau G, tau M, tau. We're going to leave it at that. Which torques balance which? Okay, you have tau balanced by tau M plus tau G. These two would rotate the beam if they were allowed. If this is fixed and the beam can rotate in either direction about that fixed pivot, tau G and tau M would rotate it clockwise, balancing the tau. These funny looking T's are called taus, right? Now, I mean, we could write the expressions in if you want. You've got everything in these expressions. You've got F, even though I didn't write it in, it's 2000. The only thing you don't have is this. You don't have M. It's the only thing you don't have. So you'll be able to solve for it. I'll write it in, but you have F times, right up here, F times sine of 78. That's 2000 times sine of 78 times 2. You can reduce that further. Tau M, M, you don't know. I'll write it in red. G is 9.81. I'm just copying this out here. Times the sine of 60 times 2. You can simplify that further. Plus tau G, which is 9.8 times sine of 60. You can reduce that further as well. So that's the only thing you don't have. The M. You can solve for everything else. Everything else in purple is some number. So you can solve for the M. Okay, so now we're going on to circular motion. Okay, so I'm going to draw a picture. I want you to find, here's one of my magic circles. Oh, that didn't work out. Okay, there's my magic circle. I want you to analyze 2 points, point 1 and 2. Point 1 here, I want you to find, whoa, what happened? I want you to find the direction at point 1 and 2 for the force, the centripetal force, velocity, acceleration. Okay, so the force, let me just centripetal force, centripetal acceleration, and velocity. Draw it for each of those corresponding points, point 1 and 2. What are the directions? And what is constant? In uniform circular motion. You do 3 and 4 as well. Yeah, you know what? I'll get even fancier. Do 3, add on 3 there. That's position 3. Okay, so I'll do different colors. So FC is in purple. AC is in red. And then V is in black, or gray black. So FC for each is always pointed towards the center. Here's the center. That's FC. FC will just be purple. I'll just go by color so you. Well, the center should be roughly there. So the purple is FC. And it is constant. It would be drawn. I tried to draw each of the arrows of equal length. It's constant because you're moving with a constant speed. Uniform circular motion means constant speed. That is brought about with a force of constant magnitude. Okay, AC is going to be in red. It's in the same direction as the force. Okay, V is always perpendicular to the force. Notice how I'm drawing these arrows. All the black arrows equal length. That's V. It says constant speed. The same length of arrow means it's a constant speed, not a constant velocity because the direction's changing. We're talking about all the magnitudes of these vectors are equal at each point. All the red vectors are equal in length, indicating a constant acceleration in magnitude, not in direction. So where does that follow from mathematically? If you're moving with a constant speed, AC is equal to V squared over R. R is constant. V is constant. That's what it means to be traveling with the uniform. When it says uniform circular motion, it means constant speed. The acceleration is constant. Okay, and then therefore FC, which is equal to MAC, is constant. In magnitude, not in direction. Okay? Okay, so let's take a look at this. Let's say you got a loop. That doesn't work. Let's say you're dealing with the loop problem. Going around this loop. You have a person at a cart. How come it's not? That's bad. Draw the free body diagram for each of these, for position 1 and 2. And relate it to the centripetal force. So number 1, draw free body diagram. Okay, and relate those forces, whatever the forces are in the free body diagram, relate those forces to Fc, the centripetal force. And then I'll have you do the same thing for a second diagram here. Okay, so draw a free body diagram for these two diagrams, these two scenarios, scenario 1 and 2. And then relate those forces in the diagram to the centripetal force. So for the first one, you have for position 1, you got Fg. And the normal force, both acting down. So the centripetal force in that case is just Fg plus Fn. For position 2, you got Fg. Fg is always pointing down in all these diagrams and all the diagrams with any free body diagram. Always pointing down. What's pointed up? I need more room here. This is scenario 2. G is pointed down. Let's point it up. Yeah, it's a different Fn. Whoa. Call it Fn2. This is Fn1. So the centripetal force in this case is Fn2 minus Fg. Okay, and they are equal. This Fc is the same as this Fc. They're equal. What are they both equal to? What is Fc? It's just another type of net force. What's net force always equal to? Yeah. So we have, for above there, we have MAC is equal to FG plus FN. And for the bottom one, we have MAC is equal to FN2 minus FG. We have that. That should help you out. Those are your expressions you'd start off with for any sort of problem involving those scenarios. For this scenario here, if FC is equal to, well, let's draw the free body diagram first. Free body diagram here, FG always is acting down. What's acting up? Smaller vector, Fn, it's not as big. So the centripetal force here is just Fg minus Fn1. What about scenario 2? If Fg is always pointed down, but the normal force in this case must be bigger than Fg. Has to be, in order to overcome it. Centripetal force in this case is Fn2 minus Fg. Fc is always Ma. Those are your equations you'll start off in scenario 2. That didn't help. This should be 1. Okay. What's equal here? Find in scenario 2 and then go back to scenario 1. Start with scenario 2 since it's right in front of us. What's equal? What are the quantities that are equal? You're assuming that the speed here is the same as the speed here, the same as the speed here. Same thing about speed here, same as the speed on top. You're assuming uniform circular motion. What's the same? Well, this is the same. This and this are the same. If it's moving at constant speed, what does that mean? That means this, I'll box it. This and this are the same. Go back to here. What's the same here? This and this are the same because acceleration is the same for both top and bottom. Because the speed is the same. Acceleration is v squared over r. If the speed is the same, the acceleration is the same in magnitude. Okay. Okay, satellite in orbit. Constant speed. What is, you know this, you always know this. If something's moving with the centripetal force, I'll just put FC. FC, then you know that's related to mv squared over r, or 4 pi squared r over t squared. But let's just work with the v squared over r. For an orbiting satellite, what's the FC equal to on the left? Write that out. Okay, so this is going to be for a satellite. You can always relate this to any satellite, whether it's a moon around a planet or an actual satellite around a planet. Same equation. What's causing something to move in a circular path as opposed to a straight line path in space? What kind of force? Gravity, which is GMM over r squared. Oops. Okay, so what's the big M? What does the big M represent? Mass of the planet, or in this case, the Earth. Yeah. So small m cancels out. You don't need the mass of the satellite. Small m is the mass of the satellite. You just have big M. You simplify this further. So r squared on the bottom on the left. Yeah, one of the r's cancels out. So you get gm over r is equal to v squared. That's your equation. I mean, you can simplify it. You can solve for the mass. You can solve for the speed. Take the square root. You can solve for the distance. Cross multiply and then divide by v squared, right? This is the general equation. You can solve for any of the things you need for a satellite. I would just write that down. The moment there's a question on this, if in doubt, start with this equation. I mean, show how you derive it. You have to show how to derive it. But that's your satellite equation, simplified form, yeah? I sometimes show more than you have to show me what you start off with and what cancels out, yeah. So that's your satellite equation. Yes, you can simplify it further. Well, practice from there. Practice solving for V. Practice solving for R. Practice solving for big M. Again, what's big M? Mass of the central body, the planet. What's causing the satellite to stay in orbit? That's what the big M is. R is the distance from what to what. Yeah, the center of the planet to the satellite. Center to center. Okay. Okay, I'll do one more problem. It looks like I'm going to have to continue this afternoon on with circular motion. I did some electrostatics with you, but that would bring us to finishing off with magnetism tomorrow morning's class. So that will be done by tomorrow morning as far as review. I have to do one more review on the weekend, focusing on conservation momentum, 2D problems. Okay, so we'll do it that way. We'll just do one. We're not finishing circular motion. That won't be till this afternoon's class. So I'll have 2 recordings for today. Saves us time. Okay, so let's say this is the Earth. Well, that doesn't look like an Earth. That's an Earth. Okay, you're gonna lift this. It's a fat rocket. Thanks. Fat rocket. You're going to do work to lift it from here to a point P. Better change color. This is a bad color. So from here to here, point P. A distance of 1,000 kilometers above the surface, not from the center, above the surface. That's key. This is the Earth. How much work is required? Now you need to know, let's say the mass of the satellite is 10,000 kilograms. Yeah, what's the work to lift it to point P? Don't tell me. Let's see if you can get started on that. Oh, we're almost done. I gotta have to finish this in this afternoon's class. So I'll save it till then. I'll finish then. Okay.